All right, so we're going to play around with graphing. We looked at graphing on number lines already. Pretty straightforward plotting point on the number line. So now we're going to break into two-dimensional data. And so identifying, for example, a point 2, 3 means go right 2 x value and then go up 3 for a y value. And we're going to look at some basic problems like this, but really we're going to do some more interesting problems related to work we did in the last few lessons where we looked at population change. Okay. So I have some data from the census information from the United States, and this is rounded to make it a little bit easier, but in 2000, the population of Washington State was about 5,900,000. In 2010, the population was about 6,700,000. And so then we look down and we can graph that. So here are those 2 points plotted. And we'll make a chart like this in our spreadsheet. And spreadsheets are nice because they will automatically label information for you, which is kind of nice. So here, the same information plotted out. So we have in 2000 population just under 6 million, which was 5,900,000 right there. And then in 2010, we're over 6.5 million at 6,700,000 over there. So the first thing we're going to do is we're just going to guess at how the population changed from 2000 to 2010, and we're well beyond 2010, right? We're way out here right now. So what you're going to do is you're going to kind of make an estimate of where the population is around now in 2018-19, and then draw a line through these points to the best of your ability. So just draw a line. Don't worry about it too much. Just go for it. No right or wrong answer yet. So there's my line. So if my line is correct, then in 2018, the population was around 7.5 million people. Okay, but I have no idea if it's correct. I'd have to go and see what latest estimates are in Washington. And that data actually, nobody's probably counted everybody in Washington. In 2020, we're going to do another census, and so we'll get some more accurate data. And so then we can maybe get a better idea, but we're not going to know that for another couple of years. Now, here I have kind of a straight line going from here to here, but it may not have done that. It could be the population dropped a little and then rose a little over time. So maybe the population did something more like this. Maybe it was steady for a little bit, and then it went up, and then it went down, and then it went up, and then it came here, and then maybe it's steady for a while, maybe. So there's lots of different possibilities. The next thing you're going to do is draw 5 different possible ways the population could change. So there's one for me. Maybe it's going to do something like that. Maybe it's going to do something like this. Maybe it's going to do something like that. So we don't have all the data, so there's lots of different ways a pattern could be formed here. Some of them are easier to find than others. We're just messing around. We're going to get a little more serious next. If we check out the next bit that we're going to look at.
Wait, so that's so what we just did is into 2, 3, 4.
Yep. So next, we're going to consider the idea of absolute change versus relative change. So think back to the work we did before. How do you find absolute change? Absolute change is just how far apart are they? Find the distance. Okay, so we just whip out a calculator and we calculate what is 6,700,000 minus 5,900,000.
$800,000.
Okay, so to get from this, oops, let me switch colors. There we go. To get from this population level up to that population level, it's a jump of plus 800,000. Okay. That's again what we call the absolute change. And that's just the new value minus the old value. So here we are at 6,700,000. Suppose that Washington State's in the prediction is they're going to get another 800,000 people, the same absolute change over the next 10 years. Okay. So 10 years later, in 2020, they're going to jump up by 800,000 again. So if I add 800,000 to 6,700,000, right, same absolute change, what am I going to get? I think I get 7,500,000. Yeah, so that's going to put me exactly right there, 7,500,000. So that's another jump by the same amount, right? By that 800,000. So what happened is to get from this point right here to that point right there, as time went by for 10 years, the population went up by 800,000. And then we just did that same thing again. We said, okay, let 10 years go by again. And then let the population go up again by 800,000. Now, when we do that, when we use the same absolute change over and over and over, we get a nice straight line. And that change that we looked at, so if we take our absolute change and divide by the change in time, so in this case, that's 800,000 people divided by 10 years. If you look at it as a fraction, that fraction is called slope. And if you have a constant slope, you get a nice straight line. So in a little bit, what we're going to do is we're going to throw that in a spreadsheet just to confirm that straight line. By throwing in some more points in the spreadsheet will just make that happen easier. Now, sometimes instead of talking about the absolute change, the population went up by 800,000 people. Sometimes we talk about it in terms of percentages. Okay, so we're going to look at percent change, which is also called relative change, in the next graph. Let's get a copy of this again. So now I'm going to take a look at relative change. So relative change is always the ratio of the absolute change divided by whatever the old or original amount was. So another way to think about relative change, absolute change is new minus old, and then we take that difference and we divide by whatever the old one was. So in this case, our new minus old was 800,000. Our old was 5,900,000. And so we just want to see what that is as a percentage. Calculator time. I'm going to take my 800,000 to divide by my 5,900,000. And the computer says that's about a 13.5, 13.6% change if we round to the nearest tenth of a percent.
This is approximately, so wave the equal sign, 13.6%.
So we talked about percent change and percent multipliers before.
So this is the percent change.
So if we were to take that percent change and multiply it by our 5,900,000 and then add that back on, that's going to give us the new amount of 6,700,000. And we could do the same thing there. We could take that 6,700,000, multiply it by 13.6%. That's going to jump us up to some new number that we're going to find somewhere over there. Other way to think about that is in terms of what's called the growth multiplier, which we looked at before. To change from a growth multiplier to the percent to the multiplier, you just add 100% to it. So the growth multiplier here would be 113.6%, or as a decimal, 1.136 about. So let's just test that out and see if it works. Back to my calculator. So if I take my initial population, which was 5,900,000, and I multiply it by my growth multiplier, which was 113.6%, or 1.136, I should get about 6,700,000. Right? That's the prediction. We're predicting it will grow by that much. The 1 means start at 100%. And so I get 6,700,000. Oh, it's a little over. How come we ended up a little over, not exactly 6,700,000? Yeah, because we rounded the 1.36. It was 1.3559, blah, blah, blah. Since we rounded, we're not going to get exactly the same answer. But the nice thing about the growth multiplier is in one step, it gets you to the new number. Okay? So let's consider the 2010 population. It was 6,700,000. So if we multiply that by the growth multiplier, 1.136, this gives us the prediction of the population another 10 years later. Okay, so that's going to put us in 2020, our relative change. So this time it's 7,600,000. So it's more than what the relative change, the absolute change said it was going to be. So absolute change and relative change give different models. So according to the relative change model, over here, we think now the population in 2020 is going to be 7 million, and let's just round it to 600,000. Which is going to put us a little higher than we were before.
Still relatively the same.
It's pretty close, but the points aren't going to line up. If we drew a straight line from here through there, this point would be above it. Okay. So what we're doing is when we look at absolute, relative or percent change, what we do is we introduce a curve to the situations. Not everything grows in a straight line. Some things curve. So there's a very, very slight curve going on right now. So we're going to whip out a spreadsheet to kind of see that curve better. So in this case, we get a very slight curve. Absolute change predicted the population in 2020 was going to be 7,500,000. Relative or percent change predicts the population will be 7,600,000. Okay. So jumping by 10 years, we're going to whip out a spreadsheet and we're going to make another prediction. What's going to happen according to each of these models in 2040? So spreadsheet time.
40. We're jumping 20 years, not 10.
Well, oh shit, 2030. Thank you. Math's a little off there. Thank you, Pat, by the way.
Thank you.
Okay, so spreadsheet
One
time.
time, it means California. It had to be one was at Disneyland.
Oh yeah.
all the rights decide to break down. I'll be Captain America then.
You have a computer with you today? Right. So I'm going to go to my quantitative literacy folder.
Yeah.
Find it. It's slow today.
It's just clean up the overhead.
Oh, yeah. All right, so winter 2019, I'm going to add new sheets, and we're going to do a bunch of tables on this sheet. So we'll add different tabs to it. As soon as you can, hop into your Google Sheets. The new sheet for lesson 2.7 on graphing. First set of graphs on sheet 1, I'm going to rename as occupation. So I'll have to set it up again. So I'll just demo it here and then we can redo it again. So let's.
Yeah, it's just having a hard time connecting to Wi-Fi.
Oh yeah.
Because it's cool.
So I've got my year, population. Year was 2000 to start with. The population was 5,900. Think about spreadsheets. I can put commas into it. A bit of a fraction of people.
You can clank it into the frame. Theory.
2010. Let's see, I want 6,700,000. Excuse me. So what's the absolute change would be, and I'm going to put it in the second cell here, would be equal to the new population minus the old population. So there's that 800,000 we talked about. Relative change would be equal to the absolute change divided by the old population. So there's that 13%. Setup.
What was the formula for the relative change again?
So the relative change is the absolute change divided by the initial population. And we want that to be percents. And usually I like 1 decimal point. Unless I need
I got
more.
12%.
Okay. So
What did I do?
did you divide by the old population or the new population? Double click on it?
20. Oh, I divided by 20.
Yes. So the first thing we're going to do is we're just going to let the population move forward. Now here, we're going to just do 10-year increments. So I'm going to write formulas for each of these. So under 2010, type equals. And then what we want to do is we just want to go previous year, excuse me. So just click on that cell and then add 10 to it. So give you 2020.
And I can highlight the first two and then just go down.
No, we're going to do that a little different. I know you could do that, but I just want to do it a different way. So instead of highlighting those two and filling down, we're just going to do a formula. So we're just going to say, hey, take the population in the previous segment, so grab that 6,700,000, and we're going to add 800,000 to that. So you just go plus 800.
Or you could just grab C3.
Yes, that's what I did.
Oh, you wrote it in, so.
So I guess, I don't want to, I want to write it in, not grab C3. There's a reason I'll talk about later. So I want B3 plus 800,000. Otherwise, what we're going to do next won't work right. All right, so now what I'm going to do is I'm going to grab both those cells, A4 and B4, and then I'm going to fill that down. And we're going to go way into the future. Let's go into 2080.
It just moved right in.
Okay, so again, to make that happen, it's a two-step process. First, you highlight the two numbers. So highlight the two numbers, let go of the mouse, and then point to that bottom right corner, and then click and fill down.
Here we go.
So into 2080, I get the population prediction is 12,300,000. Okay, so now we're going to graph this. To graph it, you just highlight both columns, including the name year and the name population labels. And then we're just going to ask for a chart. So over on the right in the toolbar, you should see a button called Insert Chart. So we go to Insert Chart. I'm going to zoom out so we can see this. Okay. First thing mine does, it says, hey, let's make a line chart. So I don't, sorry, a bar chart. So I don't want a bar chart. I want to switch. I would like to do just points for now. So I'm going to do what's called a scatter plot. So I go over and click the type and change from column chart, scroll down, find scatter plot, click. Okay. So underneath it says use column A as labels. Okay, so that means 2000, 2020, 2040, and so on. So I'm going to do that slightly different. So the next thing we're going to do is we're going to go to Customize. Over in Setup, we switch over to Customize tab. And then here, let's see, I think I want to jump down to horizontal axis. That's right. Always changing. It's not horizontal axis, maybe it's series. It's okay, I won't mess with it. All right, so we're just going to leave it. So we can just close the editor. So what we should notice here is we get a nice straight line when we do that. Okay. All right, so we're going to repeat this. We're just going to do it a little bit different. Let's see, so I think this covered up, so I'm going to click on it and move it off to the side here. We're going to make a duplicate of this screen here, and we're going to alter it just a little bit. So if you go down to where your name is at the bottom, maybe it's sheet 1 still, I'm going to make a copy. So that's duplicate, not copy 2, excuse me, duplicate. And it's going to make something called copy of, whatever it was called. That's fine. So now I'm in the copy.
Pressing duplicate?
So we're going to use duplicate. Yep. So then that jumps us into a copy of it. So we're going to mess with the copy. Now, what we're going to do with the copy is we're going to change the way we calculated the new population. So from B4 on down, I'm going to leave the years. I'm just going to get rid of those populations. So instead of using absolute change, I want to see what happens if I use relative change. Now, for the relative change to work right, I want to not use the 13.6%, but I want to consider it 113.6% to make it a multiplier. So the way we'll do that is we'll just in cell B4, zoom in again. I'm going to type equals, and I'm going to click on the previous number. So I'm going to get cell B3, and I'm going to multiply it by 113%. So to do that, I'm going to call it 1.136. I'm going to hit enter. It's going to plot another point for me over there. Then I'm going to click back on it, and I'm going to fill that down. See the difference. And I'm going to zoom out so I can see. And what you should notice is that if you try to draw a straight line from, say, this first point to that point right there, they don't line up anymore. We've introduced a curve to it.
One moment.
Okay. So you help get that done?
No,
You get the idea? Fussy computer.
no, I zoomed in, now it won't zoom out.
Control minus is to zoom out.
No, I.
I'm just going to draw a straight line here just to see that these points don't line up anymore. So this is the one where I did the relative change. Of 13.6%. Okay. The other one. All right. Take a screenshot of this. Double check that the other one lined up. Page. This one. I should see if I go from the starting point to the end point. Everything lines up perfectly. What's going on? Need help? Okay. So are you in the
That's my original one.
That's your original one. Okay. So again, back to my spreadsheet here. So my original one I had called population. That was a nice straight line. In 2080, I predicted the population would be 12,300,000. In the copy, I used the relative change instead, and there, now that doesn't have nice commas, so I'm going to fix that. I'm going to highlight those numbers, change the number format to number, and then get rid of those two decimal places. All right, so now the prediction instead of 12 million is 16 million. And generally, relative change is going to outcompete absolute change, because we have the same percentage, but a bigger base amount each time. So that data curves. And the farther you look out, the more extreme the curve is going to get. So for example, so I'm going to rename these. So my first one I called population. I'm going to call that absolute. Second one I'm going to rename, I'm going to call that relative. I'm going to make a copy of that one more time. You don't need to do this. I just want to show the extreme nature of this kind of change. And what I'm going to do is I'm just going to fill this data down way into the future. So to the year 2500. And then I'm going to delete this and regraph this data. See that. So here we were just looking in this little region over here, and the curve is very slight. But here you can see if you go too far in the future, then it gets out of control. And if you look at like the population of humans on Earth, we've been doing this kind of thing. Now, this kind of relative change is not sustainable because it starts getting too big too fast. Things crash. Okay. And so what we're going to see if we look at the world population and the US population, there's going to be a slowdown. It's going to start to curve back down or be less steep. All right, so oops, that's not it. There you go. I'm going to delete this now. So that was just, I should probably name this as extreme. All right, so that was optional. All right, so the nice thing about a spreadsheet is that if we give it a pattern, we can ask it to graph that pattern, and it does a pretty nice job for us. So what we're going to do is we're going to start taking a look at some other kinds of curves. So if you turn the page on your lesson, it is, oh, we're going to come back to the spreadsheet.
I'm just taking papers out.
There we go. So we've taken a look at absolute change gives us a straight line model. Relative change gives us a curved model. And if you come down to the next page, there's families of curves. So the main families are linear, straight line, exponential, which is the same thing as relative change, and then there's quadratic. I'm just going to make a couple of notes on those, and then we'll play in the spreadsheet with them. So I'm going to, let's see, I should label this sucker. This one right here was absolute change. That was problem number 5. This one over here, relative change, was problem number 6. This slide's a little larger. Okay. All right, new page. So we're going to have some graph families. And a graph is just a pattern according to some data. So the first family is called the linear family. And that's things like, we just took a look at, say, if we use y as a variable, 800,000 for 10 years would be about 80,000 per year, plus some starting population. That starting was 900,000. So for example, that would be a straight line equation for absolute change in the Washington population. That gave us this nice straight line.
You did 80.
Yes, and the reason I wrote 80 there is if we go back to the idea of slope, that would be the 800,000 divided by 10.
Okay.
Which is where I got the 80. Yeah, so I just cleaned that up there. Good question. And so that was the starting point. So I had 5, let's call it 5.9 million. And this graph just kind of went up in a straight line. Straight lines have a slope. And slopes have a rise and a run. So in my straight line model, my rise over run simplified down to that 80,000. So I have 800,000 over 10. Here's this number right here. So some other linear equations that aren't as much fun as this that you would see in an algebra class would be something like y equals x plus 1, or maybe y equals 3x minus 5, or y equals 1/2 x plus 2. So how do you identify a linear equation? You have a y and an x. The x has no power on it. It's not in the denominator. So it's just some number times x plus or minus some other number. That's the pattern of this kind of equation. often we write equations like this as y equals some number m times x plus b. M is what we call the slope, and b is the starting point, sometimes called the y-intercept. And the big thing about linear equations for us is linear equations represent the idea of absolute change. All right. So the other kind of family was the relative change family, and that's usually called exponential. And exponential is what we call relative or percent change. So for example, with the Washington population, we started off at 5,900,000 people. But then instead of adding 800,000 over and over again, we decided to multiply by 113.6%, so 1.136. Now, if you multiply by a number over and over again, as we did in our spreadsheet, I'm going to go back to that. Spreadsheets, relative change. So this formula said, hey, take the previous number and multiply by 1.136. What did this formula say? This formula said, hey, take the previous number and multiply by 1.136. And we just kept doing that over and over again. Repeated multiplication. Do you remember what repeated multiplication is? What does repeated multiplication mean?
Isn't it like exponents?
Exactly, it's an exponent. Yeah, so what happens here with relative changes, we end up with an exponent. So the variable x ends up in the power. Now, in this case, the y was the population of Washington. Washington today. There we go. And the x kind of represented years. In this case, it was every 10 years. So x measured every 10 years, which is a little weird. So if we put a 1 in there for x, that would be 10 years later. If we put a 2 in there, that would be 20 years later. 3 would be 30 years later. So that's the way we graphed in our spreadsheet. In exponential growth, what happens when you graph something like that is you get a curve. So you have some starting point, and then it goes up slow, but then it picks up speed and gets wicked steep. So we get this kind of hockey stick-like shape. Instead of a straight line, we get this funky curve. I'm going to call it a hockey stick. And there's a lot of different kinds of exponential functions, but the general form that we're going to see, examples, could be something like y equals 2 to the power x. Or maybe y equals parentheses 1/2, close parentheses, raised to the power x. We could even see things like y equals 2 times 3 to the power x. So order of operations there is first we raise to the power, then after we multiply by 2. So if I were to graph this blue one right here, it would look a lot like the graph of the Washington population we looked at a minute ago. This red one is a little bit different. what's going to happen to it is it's going to drop down because I'm repeatedly multiplying by a half, so I'm getting smaller over time. So if I were to look at the graph of that, it's going to look more like that. It's going to head down.
So if it's a whole number, it goes up.
If it's a whole number, it's a fractional number, it goes down.
Yeah.
Yeah. This one here, since there's a base as the whole number, that one would go up. And would curve up. All right, one more example, and then we're out of time for fun with math today. So for me, the most important things in this lesson are either something straight or it's not. If it's not straight, it might be exponential, but there's a lot of different ways to curve out there. So another.
I wanted to get that information down.
Yeah. So for another, and we're going to play more with these. There's a whole bunch of problems coming up in the worksheet. But another type of curve that we'll see is called the quadratic curve. And the shape of a quadratic curve is called a parabola.
Isn't that like U?
Yep. Parabola or parabola, how you want to say it. I'm supposed to say parabola, but I like parabola better. So quadratic, quad means 4, and 4 means 4 sides. And if you have 4 sides, that means you have a square. So quadratic means there's a square involved in it. So examples of quadratic would be y equals x squared. Or maybe y equals 1/2 times x squared. And you could have other stuff, like maybe there's a minus 2x and a plus 3. But the important thing about a quadratic is the square is the highest power of x. So that's kind of the identifying feature. So the identifying feature here is x squared. The exponential function, the identifier there is the idea of an exponential. The variable is an exponent. Okay, so that's a big idea. Variable exponents. And the linear one, the identifying there is just some number times x, maybe plus another number. So we just have x in linear, exponential, x is a power, in quadratic we have an x squared. And the quadratic shape is going to look something like this. We get this U-type shape. So for example, y equals x squared is going to have the point 1, 1, because when I square 1, I get 1. And that's a very bad scale here. I'm also going to have the point 2, 4. That's 4 there. That's enough. Because when I square 2, I get 4.
And when it's negative numbers, it just flips over and turns into an n.
If you put a negative out front, yeah. So if we graph something like y equals negative 2x squared, for example, that graph would be upside down. But it's got that U-type shape. And that shape is called a parabola. And so this lesson is about, given an equation, trying to graph one of these and identify whether it's linear, exponential, or quadratic. So we are out of time for fun for now. So keep playing around with the worksheet, take a look at the prep and the homework if you haven't already, and we'll do more of this in the next class. We only have half a class today because of the snow.